Hello everyone and welcome to week 2 of Fundamentals of Physics. In this week we're going to be going over a bit more physicsy physics. So last week we did a lot of terms and kind of definitions of, say, velocity, speed, acceleration, etc. In this lesson we're going to start with understanding kinematics. So what we're going to be doing is understanding the relationship between velocity, acceleration, and displacement, not just from a graphical standpoint, which we did earlier, but from a formulaic standpoint. And specifically, we're talking about something called projectile motion. Now, that's the motion of an object as it freely moves under gravity. You'll notice as I toss this object around and nearly hit myself in the face with it, that it appears to be moving in what we would call a projectile arc, right? Or a parabola, technically speaking. Now, this is essentially an aspect of Newton's laws that we haven't learned yet, but we will, I promise, where the object is undergoing a constant acceleration. Now, on Earth, that constant acceleration is more or less 9.8 meters per second downwards. And therefore, take any object and you drop it, it starts to accelerate downwards with an increasing velocity, right? The idea being is that acceleration is constant, and therefore velocity will change with time, and so too will displacement. Before we begin, I want you to think about how does the acceleration affect the displacement over time, right? So we take the object from rest and we drop it, and as it starts to fall down, it's going to be increasing in its speed and therefore getting further and further at a faster rate, right? What would that look like on a displacement versus time graph? So, we're going to be talking a lot about problem solving today, right? I'm trying not to kind of keep throwing this ball around, but it's too fun, right? It's 3D printed, very exciting. Behave itself, good. We're going to be doing problem solving a lot in physics, right? And in problem solving, what's going to happen is you're going to be given a question. For example, Tom has a ball, and Tom drops it from the tip of his head off to the floor. How long does the ball take to reach the ground? Now, if I'm on Earth, yes, it's a different ball. I figured you can see this one against the background a bit better. If I'm on Earth, we'd know that the acceleration is 9.8 meters per second downwards, and we would be eventually able to calculate exactly how long it would take a ball to fall from my head to the ground. Of course, you need to know how high up that height was, and I'm not going to tell you, but that's the kind of question you're going to be getting. Now, when we get a question like that, we're going to be going through 3 kind of stages, right? The first is to read and understand what the question is actually asking you, right? Now, sometimes it's a bit more complicated than others, right? So, for example, if I ask you to find the total range of this projectile, right? What that actually means is the horizontal distance, right? It means how far from one hand to the other it goes. It's not like the total kind of displacement that it gets, or the vertical. There's no vertical when we say range, right? Now I'm going to teach you all these terms. I'm going to teach you how to understand all of these principles. The second thing we're going to need to do, and that's the main physicsy thing, right, is to construct an equation or series of equations, right? We're going to use the knowledge that we have and that we're going to be generating to figure out what equations are relevant, what terms exist, so what values we already know. For example, 9.8 meters per second would be our acceleration. That might factor into an equation somewhere. And then, once we've figured out what equations we need to use and we've put in all the relevant terms that we know, we need to solve that equation in order to calculate our desired calculatable quantity, right? Now, step 2 is physics, right? Physics is where you take the natural world, you take the reality of reality, and you ascribe mathematics to it in a way that will allow you to find the thing you want to find, right? And this tracks all the way up to very, very high level physics, where essentially you're looking at, say, I don't know, a quantum harmonic oscillator. You'd be like, all right, well, that's just a Schrodinger equation inside a potential well, and you essentially take equations that match the circumstances in which you have yourself. Now, ideally, in the future, we're going to get very good at even making our own equations. And in reality, what we're going to be doing is adapting some principles to make fairly simple equations, right? But the way I like to think about it is today you're going to learn what an equation is. It's like learning what a cake is, right? I love this cake analogy, right? There's 3 stages of understanding. Knowing what a cake is, knowing how to follow a recipe to make a cake, and being able to make substitutions and make your own cake on the fly, right? So ideally, you're going to be able to construct a relevant physics equation from whatever information I give you, provided it's within reason, right? Provided it's one of the questions that we kind of focus on here in this course. But before that, we actually need to know what the equations are, right? Before we can sprint, we must run, and before we can run, we must crawl. And to crawl would be to see the equations. Unfortunately, I've got a couple of upcoming questions. So we're going to take a look at these questions a little later. These are the kind of things that you're going to be able to solve using projectile motion. So a rock falls from a 150 meters high cliff. How long does it take to hit the ground? A car's velocity changes from 30 kilometers per hour to 60 kilometers per hour in 2.3 seconds. What is the acceleration of that car? Etc., etc. You can read these. You can pause the video and read it if you want. Right? But here is our cake. Here are the equations, right? Observe the 3. These are the 3 projectile motion equations. And I drew some little smiley faces because I want you to be happy that we finally arrived at some mathematical equations. So there are exactly 3 of them, right? And we're going to go through them one by one. This is the first one. Now, an aside, right? Actually, I'll go back to the previous one, right? We've got some terms here that you've seen before. And there's 2 things that I want to point out. Right? The first thing is that acceleration here is assumed to be constant in all cases. Okay? We will only ever deal with cases for which acceleration is constant. And that means that speed or velocity can vary with time and displacement can vary with time. But we cannot have acceleration varying with time. That is illegal. If that happens, you call me, right? And I will come and I will find whoever gave you a question that has a variable acceleration. Now, the second thing is you'll notice that there are no vector hats on these equations, right? And that is for 2 reasons. The first is that we're going to begin with one-dimensional motion, right? We're going to begin with motion along a line, right? We're going to begin where you can either be going forwards or backwards. We're not going to be dealing with 2 dimensions just yet, although we will get there. And you already know most of it, so don't sweat it too much. But what we are going to also do is adopt a sign convention. We're going to say that one particular direction is positive and one particular direction, i.e. the opposite to that, is negative. And what this is going to mean is that the positive and the negative in front of a number will tell us the direction. For example, let's say that acceleration A is 9.8 meters per second squared down, right? Well, we could adopt a sign convention that says up is positive and down is negative. And if we adopted that sign convention, then what we would be really saying is A, that's an A, not a D, I'm sorry, my handwriting's bad, is equal to minus 9.8 meters per second squared. That's what that's saying, right? That minus carries information. It tells us that down, well, it tells us that the acceleration is in the negative direction, and we previously specified that the negative direction is down. Now, a note on sign convention, you don't have to pick any particular sign convention. You can pick whatever you want as long as you are consistent with it, okay? You must stay consistent. You must use the same sign convention throughout the entire question, okay? If I were calculating how long it takes a ball to hit the ground, right? And I decided that down was negative, and then halfway through, I decided that up was negative, all of my numbers are not going to play nicely, okay? So if you pick a sign convention, or when you pick a sign convention, please make sure that you keep it at at a consistent level. Okay, now let's look at our equation, right? Here's our first one, V equals U plus AT. So what are all these terms? Hopefully you've seen you've seen V before, right? Right? This is velocity. This, A, is acceleration. This t is time. But what in the world is u? Right? U is also velocity. And you might ask yourself, what the heck? How can there be two velocities? Well, there's two time periods in which we're considering things. There's the velocity before things happen, so we'll call this the initial velocity. And there's the velocity after things happen, which we'll call the final velocity. Man, it really hates my handwriting today, eh? The final velocity. Okay? So our convention is usually that u, which is the letter before v, get it? It is, good, just double checking. U is the initial velocity. It's the velocity before things happen. And v is the final velocity. It's the velocity after things happen. A is the acceleration. It is constant. And t is the time over which the things happened. Okay? Let's do a couple of examples. A car is accelerating from rest with an acceleration of 3.2 meters per second. It accelerates for 3 seconds. What is the final velocity of the car? So we're accelerating from rest. From rest implies that our initial velocity is 0. The acceleration is 3.2, so we have a equals 3.2. Notice what I'm doing, I'm just writing every little variable down, okay? It accelerates for 3 seconds, which means our activity takes 3 seconds, t equals 3. And finally, we're being asked for what v is. So we have our formula here. We're going to do v equals u plus at, which in this case, we don't need to rearrange because v is the subject. We're looking for the final velocity, v, which is 0 plus, now, sign convention, right? Let's assume that forwards is positive, so everything's positive. 3.2 times 3, which is 9.6 meters per second. Very cool, very slay. Another one. How long does it take an object in free fall of an acceleration at 9.8 meters per second to reach a speed of 100 meters per second, assuming no air resistance? Well, that's an interesting one. We're being asked for a time. Okay, so this is the question. We read the question and we need to construct our equation, right? We need to pull out the variables from it. So we're being asked for time. We want to know what time is. We're being told that acceleration is 9.8. We're being told that our initial velocity is 0. We're actually not being told that. It's kind of implied, though. And this is one of the things when point 1, read and kind of comprehend the question, there are semiotics of physics that are kind of baked into questions like this. And in this case, it's starting from rest. We've got t, we don't know what t is. We want the final velocity to be 100 meters per second. And again, this is all in the same direction, so let's assume everything to be positive. So we're now looking to solve for t. So we're going to take the equation and rearrange it for t, right? T is equal to v minus u over a, right? So subtract u from both sides, divide both sides by a. And in that case, it's going to be equal to 100 minus 0 over 9.8. That's going to be a number. Oh, I almost did 100 minus 0 divided by 9.8. That would have been really bad. Anyway, we get 10.2 seconds or so. There you go, right? You can answer these sorts of questions now. Let's move on to the next equation. Number 2, S equals ut plus 1/2 at squared. Now this has got a fair few things in it. Right, let's record down the ones we already know. U is the initial velocity, okay? It's the velocity when the activity begins, when time starts, right? it's the velocity, technically, it's the velocity at t equals 0. It's right, when time is 0, that's the velocity that we're considering. Right, t here and here is time of activity. It's uncalibrated. How exciting. And a here is the acceleration, which we know. So what is s? Well, it's displacement, right? It's displacement, and it's the displacement, wow. Pretend that says displacement, please. It's the displacement from when time begins, okay? So it is the change in displacement from t equals 0 all the way to whatever the final time is, until the journey is over, okay? So, as an example, a ball is dropped from a cliff of height 100 meters. How long does it take to hit the ground? That's a harder one. We'll do the first one. We'll do the second one first, right? But that top one is a very common type of question. But I want to do a simple one first, where we don't rearrange. We've got a car starts from rest, so we've got initial velocity equal to 0, an acceleration of 3.2 meters per second. So a equals 3.2. We've got t equals 10, and we're being asked to figure out how far it goes forwards. Now again, everything's in the same direction so far, so we're just going to consider the magnitudes. Right? We've got s, which is what we're looking for, the distance traveled, is equal to 0, score, we don't have to do any maths, plus 1/2 times, I almost wrote 9.8, times 3.2 times 10 squared. Pop that in the old calculator. 0 plus 1, I was about to say 0 plus 1.2. So 0.5 times 3.2 times 10 squared gives us 160 meters. That's how far it goes, 160 meters. All right, let's try a third one. A ball is dropped from a cliff of height 100 meters. How long does it take to hit the ground? Now this one is a bit more complex, right? We have a ball dropped from a cliff, and therefore there are some assumptions inherent in the language that we're using. First of all, dropped implies an initial velocity of 0, right? Dropped implies being dropped from rest, whereas thrown is when you have an initial velocity, ow, on it. Oh, I just hit myself on the eye. Oh, but I'm keeping going for you, for my physicists. This better have been recorded. Oh. All right, so our initial velocity is 0, right? Because the ball is dropped, not thrown. The height, right? We are going to have our ball, let's draw a cliff face. The ball is traveling down 100 meters. So if we decide that down is positive, right, which we can do, then s equals 100, right? Because the total distance that this object is going to travel is 100 in the positive direction. I've decided down is positive. So then we have our acceleration, and again, it is assumed to be 9.8 meters per second. Now, meters per second squared, I should say. My eye's really hurting. So this is assuming, of course, that we're on Earth, which if they haven't told you, you generally assume that you are. I assume that I am on Earth every single day. And also, because we denoted down as the positive direction, then 9.8 becomes or stays plus 9.8, right? It's not negative, even though it's down, because we decided down was positive. Okay. Now we're being asked for t. And I want you to understand that if u was not equal to 0, solving for t would be really annoying. We'd have to use quadratics, and I don't want to do that. So instead we've got a u equals 0 problem. So we want to rearrange for t, But first, let's write in some values. We've got 100 is equal to 0 plus 1/2 times 9.8 times t squared. And now we can rearrange for t. Okay, so t is equal to, well, let's say t squared is equal to 100 times 2, because divided by 1/2, divided by 9.8. And that means t is equal to the square root of that, which will be some number. Let's see. .517 seconds. Now, I put too many decimal places there, but that's fine. Okay, and now for our third and final equation. V squared equals u squared plus 2as. Now, this you can actually get from substituting each of the equations that we've just done into each other, right? So this is not any new information. But it is a useful equation because it avoids time, right? You don't need to solve for time of flight or time of, journey. So v squared equals u squared plus 2as. This is, for example, a car has an initial speed of 30 meters per second, and it needs to brake in 10 meters. What must its acceleration be? Now again, you should know all these terms already, right? V is the final velocity, right? U is the initial velocity. A is the acceleration. And S is the distance traveled during the journey. So S is the distance traveled from the time where we had our initial velocity to the time where we have our final velocity, okay? I say time, even though we're not actually using time, right? But it's the distance between the two measurements, let's say, of velocity, right? Where you measure your initial velocity at some point, you measure your final velocity at some other point after some traveling has been done, and S is the distance of that travel. Now, this equation is one where it's really important to get your signs right, because A and S will have either the same or the opposite sign, and that will dramatically affect the outcome of this equation. This is the one that the mistake is most often made of getting the signs wrong or using inconsistent sign convention. So let's say a car has, and now you might be looking at that question going, Tom, how does that one work? Ignore it. That's how. A car has an initial speed of 30 meters per second. Right, let's start recording all of our little terms. So we've got initial speed of 30, and it needs to, oh, that's not a rubber, brake, i.e. come to 0, and I think I spelled brake wrong. I meant to say the one where you slow down, right? In 10 meters. What's its acceleration? So there's a few assumptions here. The first is that we want the final velocity to be 0, okay? We want the car that was at 30 meters per second to come to a final velocity at 0 meters per second. The second assumption is the direction. So let's assume, or let's decide that the positive direction is forwards, which means that the initial velocity is plus 30. The final velocity is still 0, that doesn't really change. But the acceleration must be negative because it's going to be slowing down. Therefore, the acceleration is in the opposite direction to motion. And then in addition to that, the distance traveled. When you brake in your car, if you drive, I didn't drive at your age, so no sweat. But when you brake in your car, what you are going to be doing is traveling forwards as your speed decreases. So the displacement is a positive 10 meters, even though we want to be braking, right? And that's the only way this system is going to work. Let's look at our equations. We're going to have 0 squared is equal to 30 squared plus 2 times a times 10. And what you will notice is that the only way that 30 squared plus something can equal 0 is if A is negative. That's the only way this maths can work out to give us 0 at the end. And that's why it's very important to get your sign conventions correct, because if you accidentally make both of them positive or you forget which one's supposed to be which, you'll end up with an impossible answer. So in this case, we have A is equal to 30 squared, sorry, negative 30 squared divided by 2 times 10. Let's calculate that. Negative 30 squared divided by 2 times 10 yields us negative 45 meters per second squared. Now, you can tell I made that up because that would kill you, right? That's nearly 5 Gs. What a fool I am, right? That's what you get for just making up random numbers, right? In reality, you shouldn't stop. That tells you why you can't go very, very fast, right? Because if you need to brake, you won't be able to, right? I think the maximum deceleration of many cars is, what's 4 meters per second squared, so that's a lot. Anyway, those were the 3 equations. Please complete some of the questions down below on your utilization of these 3, and I'll see you in the next video where we'll discuss a little bit more about these equations. Thank you so much for watching. I'll see you in the next video.